Picture staring up at the night sky, your eyes tracing the countless stars scattered like glitter across an endless black canvas. It feels peaceful, familiar, but the truth is, the universe is anything but simple. Out there, beyond what our eyes can see, lies a realm of mysteries so profound that even the brightest minds on Earth still grapple with them. We've sent probes to distant planets, built telescopes powerful enough to peer billions of years into the past, and yet space refuses to give up all its secrets. It humbles us. For every question science answers, a dozen more emerge, each more baffling than the last. Think about this. We live in an age of staggering technological advancement, where artificial intelligence can compose symphonies and robots roam the surface of Mars. But despite all that, some of the most fundamental questions about the cosmos remain wide open. What's hiding in the unfathomable darkness between galaxies? Why does 95% of the universe consist of stuff we can't even detect, dark matter and dark energy, whose very existence defies our understanding of physics? And perhaps the most haunting question of all, are we truly alone, or is something or someone else out there watching from the shadows of the infinite? This video is a journey into those uncharted territories, the questions that keep astronomers awake at night. We'll explore 30 of the most perplexing enigmas of space, the ones that defy logic, challenge our theories, and remind us just how much we still have to learn. Some of these mysteries might shake your understanding of reality itself. Others will leave you in awe of the sheer scale of the unknown. But one thing's certain, by the end, you'll see the night sky differently. So let's dive in, because the universe isn't just stranger than we imagine, it's stranger than we can imagine. What if I told you the biggest mystery of the cosmos isn't just how the universe began, but what existed before it? The Big Bang Theory gives us a stunning origin story, a fiery birth of space and time around 13.8 billion years ago. But here's the catch: the moment of the Big Bang isn't the true beginning. It's the edge of our understanding, a boundary where physics as we know it collapses. So what lies beyond that edge? Some scientists propose a dizzying idea. Our universe might be just one bubble in an infinite cosmic foam, where other universes with entirely different laws of physics constantly pop into existence. This is the multiverse theory, where quantum fluctuations, tiny, unpredictable ripples in the fabric of reality, could spawn new universes endlessly. Imagine blowing soap bubbles in a breeze. Some float away intact, others pop instantly. Could our universe be one of the lucky ones that stabilized? Then there's the cyclical model, suggesting an endless loop of universes expanding and collapsing, like a cosmic inhale and exhale. Picture a phoenix dying in flames only to rise again, except here, it's spacetime itself reborn. But even these theories hit a wall. Without time or space as we understand them, the very concept of before might be meaningless. Our language, our logic, even our math, they're all built for a universe with rules. Beyond the Big Bang, those rules might not apply. That's the haunting beauty of this question. It forces us to confront the limits of human knowledge. We're like ants trying to map a continent we've never seen, armed only with a single grain of sand as our guide. Every answer we propose raises new questions, deeper and stranger than the last. And that's why this mystery endures. It's not just about the universe's birth. It's about whether we'll ever truly understand the cradle it came from. We take for granted that the universe is vast, but is it truly endless? This isn't just philosophy. It's one of the most heated debates in modern cosmology. On one side, the cosmic microwave background, the afterglow of the Big Bang, hints at a universe so immense it might stretch forever. Those faint temperature variations in the ancient light. They suggest a flat geometry, like an infinite sheet of paper extending in all directions without curving back on itself. If that's true, no matter how far you traveled, space would never loop you back home. Yet there's a twist. Some measurements of the universe's curvature don't quite add up. Imagine blowing up a balloon with tiny dots on its surface. As it expands, dots move apart, but if you could see far enough, you'd notice the surface curves. Some scientists argue our universe might be like that balloon, finite but unbounded. Travel far enough in one direction and theoretically you'd end up where you started. It's mind-bending, but so is the alternative, infinity. Here's where things get messy. Even our best tools have limits. The cosmic microwave background gives us a snapshot of the early universe, but like trying to map an entire forest by studying a single leaf, it leaves room for interpretation. Then there's dark energy, that mysterious force accelerating the universe's expansion. Could it be stretching space into infinity, or is it just another clue we haven't fully decoded? The truth is, we're trapped in a cosmic catch-22. To measure the universe's shape, we'd need to see beyond the observable horizon, the farthest light that's had time to reach us in 13.8 billion years. But by definition, we can't. It's like being stuck in a lighthouse trying to guess the ocean's size by the waves you see. So why does this matter? Because infinity isn't just a number, it's a paradigm shift. A finite universe implies boundaries, cycles, maybe even a destiny. An infinite one, that's a void where anything that can happen will happen given enough space. Somewhere out there, an exact copy of you might be reading these same words, or maybe not. And that's the thrill. The universe keeps its ultimate secret close, leaving us to wonder if we'll ever truly know. Right now, as you read these words, you're surrounded by an invisible ocean, a mysterious substance that outweighs all the stars, planets, and galaxies we can see by a factor of 5 to 1. We call it dark matter, and its existence isn't just a guess, it's written into the very fabric of the cosmos. The story begins in the 1930s when astronomer Fritz Zwicky noticed something bizarre about galaxy clusters. They were moving too fast. According to the laws of gravity, these clusters should have flown apart long ago unless something unseen was holding them together with its gravitational glue. Fast forward to the 1970s, and Vera Rubin's groundbreaking observations of spiral galaxies sealed the deal. Stars at the edges of these galaxies were orbiting just as fast as those near the center, defying Newton's laws. Imagine spinning a vinyl record. The outer tracks move faster than the inner ones, but in galaxies, it's as if the whole record spins as one solid piece. The only explanation, an invisible halo of matter, it's gravity keeping stars from flinging into the void. But dark matter's fingerprints don't stop there. Look at the way massive galaxy clusters bend light from objects behind them, like cosmic magnifying glasses. This phenomenon, called gravitational lensing, reveals even more hidden mass than what's visible. In some cases, the distortion is so extreme it creates mirrored images of distant galaxies, stretched into glowing arcs, a celestial funhouse mirror we couldn't explain without dark matter's unseen hand. So what is this enigma made of? The leading suspect for decades has been WIMP, weakly interacting massive particles. These hypothetical particles would barely interact with normal matter, passing through you right now like ghosts through walls. Scientists have built elaborate traps deep underground, shielded from cosmic noise, waiting for a single telltale collision between a WIMP and an atom. After decades of searching, the detectors remain silent. Then there are actions, ultralight particles born from theories trying to solve unrelated quantum puzzles. Billions could be streaming through your hand every second, yet they'd feel like a gentle cosmic breeze. Recent experiments using powerful magnetic fields have hunted for their faint whispers, but so far, nothing conclusive. The frustration grows when you consider the alternatives. Could dark matter be primordial black holes forged in the chaos of the Big Bang, or an entire shadow universe with its own particles and forces, forever beyond our perception? Every dead end forces us to rethink our assumptions. Maybe dark matter isn't one thing but many, a mix of strange particles we haven't even dreamed up yet. Here's the humbling truth. We've mapped its gravitational shadow across the cosmos, built machines to catch it, and written equations to predict it. Yet after nearly a century, dark matter remains the universe's ultimate hide-and-seek champion. And that's what makes this mystery so thrilling. It's not just about filling a gap in our equations, it's about discovering an entirely new layer of reality, waiting just beyond the reach of our senses. If the universe played fair, we shouldn't exist. Here's why: every particle of matter has an evil twin antimatter, identical in mass but opposite in charge. When they meet, they annihilate in a flash of pure energy. According to the Big Bang, matter and antimatter should have been created in equal amounts, leaving nothing behind but a sea of radiation. And yet, here we are, stars, planets, you, me, all evidence that somehow matter won the cosmic lottery. This is the puzzle of baryon asymmetry, and it's one of physics' greatest unsolved riddles. The first clue came from deep underground. In the 1960s, experiments studying subatomic particles revealed something bizarre. Certain reactions involving weak nuclear force didn't mirror perfectly when flipped, like a reflection in a funhouse mirror that subtly distorts your image. This phenomenon, called CP violation, showed the universe has a tiny but crucial bias favoring matter over antimatter. But here's the kicker. The amount of CP violation we've measured is 1,000,000 times too small to explain the overwhelming dominance of matter today. It's like finding a single grain of sand and realizing an entire beach is missing. Enter leptogenesis, a theory so elegant it almost feels like science fiction. Picture the early universe as a superheated soup where heavy, hypothetical particles decayed unevenly, producing slightly more electrons than anti-electrons. These extra electrons then triggered cascades of reactions, tipping the scales toward matter. But proving this happened, that's another story. These particles would be far too massive for our current colliders to detect, lurking at energy levels we can't yet reach. Then there's the multiverse angle. Some theorists suggest our universe is just one of countless bubbles, each with random imbalances, and we're lucky enough to live in one where matter prevailed. It's a dizzying thought. Our existence might hinge on a quantum roll of the dice we'll never see. What makes this mystery so tantalizing is how fundamental it is. Solve baryon asymmetry, and you might unlock secrets about the universe's birth, the nature of dark matter, even why time flows forward. Every experiment, from neutrino observatories buried under Antarctic ice to particle colliders smashing atoms at nearly light speed, brings us closer to rewriting the story of our cosmic origins. Until then, we're left staring at the stars, wondering why there's something instead of nothing. And that question, well, it's what makes science so thrilling. Gaze deep into the night sky, and you're not just seeing stars, you're looking at the edge of a cosmic cage. The observable universe stretches 93 billion light-years across, a sphere limited by how far light has traveled since the Big Bang. But here's the unsettling truth. That's not the universe. It's just the part we're allowed to see. Like a shipwrecked sailor peering at the ocean from a tiny island, our entire reality might be an insignificant speck in something unimaginably vaster. The cosmic horizon problem cuts to the heart of this mystery. No matter how powerful our telescopes become, we'll never see beyond this bubble of spacetime. The expansion of the universe pushes distant galaxies away faster than their light can reach us, creating an invisible wall. But what's on the other side? One radical theory suggests an endless fractal of universes, each born from quantum fluctuations in an eternally inflating cosmos. Picture a boiling pot of water, bubbles forming, expanding, and sometimes colliding. Our universe could be one of those bubbles, floating in a sea of others with entirely different laws of physics. Then there's the multiverse hypothesis, where every quantum decision spawns a new reality. Did you choose coffee this morning? Somewhere out there, a version of you picked tea, and both choices created branching timelines. If true, beyond our horizon could lie infinite variations of Earth, some nearly identical, others unrecognizable. But here's the kicker: these alternate realities would forever remain hidden, their light eternally outpaced by the expansion of space. Could we ever break through this barrier? Some theorists dream of harnessing exotic phenomena, wormholes stabilized by negative energy, or warp drives bending spacetime itself. Yet even if such technologies emerged, the horizon might retreat forever, like a mirage in the desert. The universe seems designed to keep its deepest secrets just out of reach. That's the paradox of our existence. We're driven to explore, to push boundaries, but the cosmos whispers a humbling reminder: some doors may stay locked. And perhaps that's for the best. After all, a universe that reveals all its mysteries at once would leave nothing to dream about. Imagine flipping a coin, not just once, but an infinite number of times. In some realities, it lands heads every time. In others, tails. Now stretch that idea across every possible event, every choice, every quantum fluctuation. That's the dizzying promise of the multiverse, a concept that blurs the line between cutting-edge physics and something straight out of science fiction. Let's start with string theory, often hailed as the theory of everything. It suggests that the fundamental particles we know are actually tiny, vibrating strings. But here's the twist: for the math to work, these strings require at least 10 dimensions, far beyond the 4 we experience. This leads to the landscape problem, where the extra dimensions could fold and twist into billions of possible configurations, each birthing a universe with its own unique laws. Picture a cosmic game of Tetris where every possible arrangement exists somewhere, and you're stuck with the one where gravity lets your coffee cup stay on the table. Then there's quantum branching, the idea that every decision spawns a new timeline. Schrödinger's cat isn't just alive or dead, it's both in separate worlds. Astronomer Royal Sir Martin Rees likens it to a constantly splitting tree, where every twig represents a new universe. But is this science or philosophy? Critics argue that if these alternate realities can't interact with ours, the theory is untestable, more metaphysics than physics. Yet tantalizing clues emerge. Some cosmologists study the cosmic microwave background for bruises, anomalies that might be scars from collisions with other universes. Others hunt for gravity, leaking into our dimension from neighboring brains, a concept from M-theory. So far, the evidence is as elusive as the universes themselves. The multiverse forces us to confront a humbling question. Are we the architects of reality, or just bystanders in an infinite cosmic kaleidoscope? Whether it's string theories, hidden dimensions, or quantum mechanics branching paths, one thing's clear: the answer rewrites not just our place in the universe, but the nature of existence itself. Time feels like the most solid part of our reality, ticking forward with relentless certainty. But peel back the layers, and you'll find it's one of the universe's greatest illusions. Newton saw time as an absolute river flowing uniformly across the cosmos, separate from space, but Einstein shattered that illusion. In his relativistic world, time bends like a rubber sheet around massive objects. A clock on a GPS satellite ticks faster than one on Earth, not because it's defective, but because gravity here stretches time itself. Imagine two friends, one stays on Earth, the other rockets away at near light speed. When they reunite, the traveler might have aged mere years while the stay-at-home companion has grown old. Time isn't just a backdrop, it's a dynamic actor in the cosmic play, woven into the very fabric of space-time. Then there's quantum mechanics, where time takes on an even stranger role. At the smallest scales, particles don't seem to experience time linearly. Quantum events can appear to happen in both directions, like watching a movie where the plot runs forward and backward simultaneously. Some interpretations suggest time emerges from the entanglement of particles, a cosmic illusion created by their interactions. Think of it like a flipbook. The individual pages' quantum states don't move, but when you flip through them, the illusion of motion and time appears. But the biggest puzzle isn't how time behaves, it's why it flows forward at all. The laws of physics work just as well if time runs backward, yet we never see shattered teacups reassemble or eggs unbreak. This arrow of time is tied to entropy, the universe's tendency toward disorder. Like a shuffled deck of cards, systems naturally move from order to chaos. Yet here's the catch: entropy only explains why we perceive time's direction, not why the early universe had such improbably low entropy to begin with. Was it a fluke, or is there a deeper principle at work? Some theorists propose time isn't even fundamental, just a useful fiction our brains construct to make sense of change. In the block universe model, past, present, and future exist simultaneously, like frames in a film strip. Your birth, this moment, and your distant future are all equally real, forever fixed in space-time. Free choice, then, becomes a haunting question. If the future's already out there, are we just passengers on a predetermined track? The more we study time, the more elusive it becomes. From the cosmic scale, where black holes stretch it like taffy, to the quantum realm where it might not exist at all, time defies simple explanation. And that's the beauty of the mystery. It forces us to rethink not just the universe, but the very nature of existence itself. Imagine throwing your most precious book into a fire. The pages burn, the ink vanishes, but in theory, if you could track every escaping molecule of smoke and ash, you could reverse the process and reconstruct every word. That's quantum mechanics' golden rule. Information is never truly lost, just scrambled beyond recognition. Now picture that book falling into a black hole. According to Einstein, it's gone forever, crushed into a singularity where space and time cease to exist. But quantum mechanics screams no, that information must survive. This clash of titans is the black hole information paradox, and it's been tearing physics apart for decades. The trouble started with Stephen Hawking's revolutionary discovery: black holes aren't completely black. They leak. Quantum fluctuations near the event horizon, the point of no return, allow particles to escape as faint radiation, slowly evaporating the black hole over eons. But here's the catch: Hawking radiation is random, like static noise. It carries no trace of what fell in. So when the black hole finally vanishes, all the information it swallowed vanishes too, violating quantum theory's sacred principle of reversibility. It's like burning a library and claiming the smoke contains no hints of the story's lost. Cue the panic. Physicists scrambled for solutions, and the first contender was the firewall theory. Picture the event horizon not as a silent threshold, but a blistering wall of energy. As particles attempt to escape, they collide with this inferno, preserving information by imprinting it onto the radiation. But there's a brutal cost. Einstein's smooth spacetime near the horizon gets shredded. An astronaut crossing wouldn't notice anything unusual in the classic model, just floating freely until spaghettification kicks in. With a firewall, they'd be vaporized instantly, violating relativity's prediction of no drama at the horizon. Then came holography, a mind-bending idea that information isn't lost because it was never really inside the black hole to begin with. Think of a hologram sticker, a two-dimensional surface that creates the illusion of three dimensions when light hits it. Similarly, the theory suggests all the information swallowed by a black hole is smeared across its event horizon like cosmic graffiti. When particles escape as Hawking radiation, they read this encoded data like a projector, revealing a hidden image. But the wildest twist: some versions of string theory propose black holes aren't pits of destruction at all. They're tangled knots of cosmic strings called fuzzballs, bristling with preserved information. No singularities, no firewalls, just a dense, fuzzy orb where data stays intact. Others suggest black holes birth entirely new universes inside them, with the information reborn in a space-time we can never access. The stakes couldn't be higher. If information can be destroyed, quantum mechanics, the foundation of modern physics, needs rewriting. If it isn't, Einstein's elegant spacetime might require a radical overhaul. After 50 years, we're still trapped between two incompatible visions of reality, with black holes as the ultimate judge. And perhaps that's the lesson. The universe guards its deepest secrets not with locks, but with paradoxes that force us to rethink everything we know. At the heart of every black hole lies a nightmare for physics: the singularity. According to Einstein's equations, when a massive star collapses, all its matter gets crushed into an infinitely dense point where gravity becomes infinite, space-time curves beyond recognition, and the laws of physics simply stop. It's a cosmic divide by zero era, a place where math screams in protest, but infinities don't exist in nature. They're signs our theories are incomplete. So what's really lurking in that unimaginable darkness? One radical alternative comes from loop quantum gravity, a theory that reimagines spacetime as a woven fabric of tiny, indivisible threads. Instead of a singularity, this framework suggests black holes might harbor Planck stars, ultra-dense cores compressed to the smallest possible size, roughly 10 to the power of -35 meters across. Picture a rubber band stretched to its limit. Just before it snaps, it resists further deformation. Similarly, a Planck star would rebound from its maximum compression, releasing energy in a cosmic echo. If true, black holes could be time bombs waiting to explode in a delayed burst after billions of years. Then there's the holographic principle, which flips the script entirely. It proposes the interior of a black hole isn't a place at all, but a projection of information encoded on its event horizon, like a DVD storing a three-dimensional movie on a two-dimensional surface. Step inside and you're not descending into a pit, you're being translated into data, your existence rewritten as holographic bits. But the wildest idea. Some theories suggest black holes are gateways. Beyond the singularity, spacetime might twist into a tunnel, a wormhole connecting to another universe or a distant part of our own. The catch: these cosmic shortcuts would likely snap shut instantly, crushed by the same gravity that birthed them. Unless, that is, some exotic form of negative energy holds them open, a material that, so far, exists only in equations. Here's the unsettling truth: we'll likely never peer inside a black hole to check. Any probe we send would be ripped apart, its signals trapped behind the event horizon. Even Hawking radiation, the faint glow black holes emit, carries no useful data about their interiors. So we're left with theories, each more fantastical than the last, dancing at the edge of what science can test. That's the paradox of black holes. They're laboratories for the most extreme physics, yet they hide their secrets behind an impenetrable veil. Maybe the singularity is real. Maybe it's an illusion, a signpost pointing toward a deeper theory waiting to be found. Either way, black holes remind us that the universe isn't just stranger than we imagine, it's stranger than we can imagine. And somewhere in that darkness, the next revolution in physics might be lurking. Ever stepped on a trampoline with a bowling ball in the center? The way the fabric stretches and warps under the weight gives you a crude analogy for spacetime bending around massive objects. Now imagine pinching that trampoline's surface so sharply that two distant points suddenly touch. That's the essence of a wormhole, a cosmic shortcut through the folded fabric of reality. Einstein's equations actually allow for these tunnels, called Einstein-Rosen bridges, where space and time bend so drastically that a passage forms between separate points in the universe. The math checks out, but the universe seems to reject them. The first hurdle is stability. Picture blowing a soap bubble. It forms beautifully for a moment, then pops. Wormholes are like that. They'd snap shut instantly under their own gravitational forces unless propped open by something extraordinary. Enter exotic matter, a hypothetical substance with negative energy density. Unlike normal matter that attracts via gravity, exotic matter would repel, acting like anti-gravity to keep the wormhole's throat from collapsing. The catch: quantum physics permits negative energy in microscopic amounts. Think Casimir effect, where two metal plates in a vacuum experience a slight push from quantum fluctuations. But scaling that up to stabilize a traversable wormhole would require more negative energy than we've ever observed. Some calculations suggest you'd need the equivalent of a neutron star's worth crammed into the wormhole's walls. Then there's the causality problem. If you could travel through a wormhole, you might arrive before you left, violating cause and effect. Relativity allows for such closed time-like curves, but they are frowned upon by physicists because they lead to paradoxes, like going back in time to prevent your own birth. Nature seems to abhor these loops, leading to the chronology protection conjecture. Some as yet unknown law of physics might actively prevent time travel to preserve cosmic order. So why haven't we found any? Wormholes, if they exist, would likely be microscopic, fleeting phenomena smaller than atoms and lasting fractions of a second. Some theories suggest primordial wormholes might have formed in the early universe's chaos, inflated to macroscopic sizes during cosmic expansion. But spotting one would require detecting distortions in spacetime far subtler than those from black holes, like trying to find a needle in a haystack when the needle is made of invisible, vibrating spacetime threads. Here's the tantalizing part: wormholes aren't impossible, just improbable with our current understanding. They linger at the edge of physics where imagination and calculation collide. And that's the thrill. The universe doesn't owe us easy answers, but it does offer endless questions to keep us searching. Think about playing a cosmic game of roulette, except the wheel has trillions of slots and only one combination wins: life as we know it. The fact that we're here to ponder this question at all is staggeringly unlikely. Tweak any of nature's fundamental constants by just a hair, and the universe becomes a sterile wasteland. Gravity a smidge stronger, stars burn out in a cosmic blink. The electromagnetic force slightly weaker, atoms never bond, and chemistry, along with you, me, and every living thing, never happens. This eerie precision is called fine-tuning, and it's one of the most hotly debated mysteries in science. Enter the anthropic principle, the idea that the universe must be compatible with life because we're here to observe it. It sounds circular, but there are two flavors. The weak version is almost a truism. We find ourselves in a life-permitting universe because we couldn't exist in one that isn't. The strong version goes further, suggesting the universe was meant to produce life, hinting at something intentional. That's where the controversy ignites. Is fine-tuning just a cosmic coincidence, or does it demand an explanation beyond pure chance? One compelling escape hatch is the multiverse. If infinite universes bubble into existence, each with random constants, statistically, a few will hit the jackpot. We're not special, just lucky to land in the one where the numbers lined up. It's like shuffling a deck of cards endlessly. Eventually, you'll deal a perfect hand. But critics argue this just kicks the can down the road. What created the multiverse? Why do its laws allow for such variety? Then there's the possibility of deeper, undiscovered physics, a master equation that locks constants into their life-friendly values. String theory dreams of such unity, but after decades, it's yet to deliver testable predictions. Others propose a cyclical universe where each iteration tweaks the constant slightly, converging over eons toward life-friendly values through cosmic trial and error. Here's what keeps physicists awake. Fine-tuning might not be a problem to solve, but a clue. Like finding a locked door with a key already in your hand, it hints that we're missing something profound. Whether the answer lies in a multiverse, a deeper law, or something beyond our current imagination, one thing's certain: the universe isn't just allowing life. It's practically rolling out the red carpet. The real question is why. The universe is unimaginably vast, with 2 trillion galaxies, each hosting billions of stars and planets. Given those odds, the cosmos should be teeming with civilizations. So why does the sky feel so silent? This eerie contradiction is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" After decades of searching, we've found no definitive signs of alien life. Not a single radio signal, no megastructures harnessing starlight, no interstellar probes drifting through our solar system. The silence is deafening, and the explanations range from unsettling to downright terrifying. One leading theory is the Great Filter, a cosmic bottleneck that prevents life from reaching interstellar stages. The filter could be behind us, meaning humanity somehow beat astronomical odds to emerge. Perhaps complex life is extraordinarily rare, requiring a perfect storm of plate tectonics, moon stabilization, and Jupiter-like planets deflecting asteroids. If so, we might truly be alone, but the darker possibility, the filter, lies ahead. Maybe every advanced civilization eventually destroys itself through climate collapse, nuclear war, or rogue artificial intelligence. In this scenario, the silence isn't a sign of rarity, but a graveyard warning. Then there's the zoo hypothesis, the idea that extraterrestrials are deliberately avoiding us. Picture humans as ants in an interstellar nature, preserve observed but not contacted, either to protect our development or because we're simply not interesting yet. Some versions suggest a galactic prime directive prevents interference until we reach a technological threshold. Others propose that advanced civilizations might find us irrelevant, the way humans don't stop to converse with every bacterium they pass. But what if the answer is even stranger? Civilizations might transcend biology, uploading their consciousness into digital realms or harnessing dark energy in ways invisible to our instruments. They could be all around us, operating on scales or dimensions we can't perceive. Or perhaps interstellar travel is simply too costly, even for advanced species. The energy required to cross light years might make physical expansion pointless. The paradox forces us to confront a humbling truth. We're either impossibly early, impossibly lucky, or impossibly doomed. Until we find evidence otherwise, the stars keep their secrets, and the question lingers, haunting our search for cosmic company. What if everything in the universe, from swirling galaxies to the tiniest quark, has some form of inner experience? This isn't science fiction. It's panpsychism, the radical idea that consciousness isn't exclusive to biological brains but is woven into the fabric of reality itself. At first glance, it sounds mystical, but some of the most respected thinkers in physics and philosophy are taking it seriously, because it might solve the hard problem of consciousness. The hard problem, coined by philosopher David Chalmers, asks why physical processes in the brain should feel like anything at all. Why isn't the brain just a silent, self-operating machine? Neuroscience maps neurons firing, but no one can explain how electrical impulses translate into the vivid redness of an apple or the ache of nostalgia. Panpsychism offers a wild alternative. Maybe consciousness isn't produced by the brain, maybe it's always been there, a fundamental feature of the universe like mass or charge. Now tie this to quantum mechanics, where particles exist in superpositions, multiple states at once, until observed. The infamous Schrödinger's cat thought experiment highlights the role of the observer in collapsing quantum possibilities into a single reality. Some interpretations, like von Neumann-Wigner consciousness causes collapse, suggest that conscious observation itself might be what nails down reality. Could the universe's quantum weirdness be hinting that consciousness isn't just a passenger, but a participant in shaping existence? Even more provocative, integrated information theory proposes that consciousness isn't binary on/off, but exists on a spectrum. A human brain has a high phi value, a measure of interconnected information making rich subjective experience possible. But a simple thermostat processing temperature changes might have a tiny flicker of experience, barely distinguishable from zero. If true, the cosmos could be an unimaginably vast network of overlapping subjective experiences, from stars feeling their own nuclear fusion to black holes harboring some ineffable form of awareness. Critics dismiss this as poetic speculation after all. How would you test whether an electron is aware? Yet proponents counter that panpsychism avoids the pitfalls of both materialism, which can't explain how matter gives rise to experience, and dualism, which struggles to explain how non-physical minds interact with physical brains. Instead, it proposes a middle path, consciousness as the hidden variable in the equations of reality, as fundamental as space-time. The implications are staggering. If consciousness is universal, then the universe isn't just a cold, mechanical system, it's a vast, thinking entity, with planets and nebulae as its synapses. Maybe black holes aren't just gravitational pits but cosmic contemplations. Maybe the Big Bang wasn't just an explosion, but the universe waking up to itself. Of course, this raises more questions than answers. How do simple micro-consciousnesses combine into complex experiences like human thought? Could entire galaxies have unified awareness? We may never know, but the mere possibility reshapes how we see our place in the cosmos. After all, if the stars themselves are sentient in some unfathomable way, then looking up at the night sky isn't just stargazing, it's one form of consciousness greeting another across the void. The moment you step outside on a clear night and gaze up at the stars, you're looking at more than just distant suns. You might be staring at the answer to one of humanity's oldest questions: where did life come from? The prevailing theory, abiogenesis, suggests life emerged right here on Earth, born from a primordial soup of chemicals stirred by lightning and volcanic heat. But there's a twist. The ingredients for that soup, water, organic molecules, even amino acids, have been found littered across the cosmos, hitching rides on comets and asteroids. So did life really start here, or was it delivered from the stars? Take the Murchison meteorite, a space rock that fell in Australia in 1969. Inside, scientists discovered over 90 different amino acids, 20 of which are used by life on Earth. Some of these molecules were even structured in ways that don't occur naturally in terrestrial chemistry, proving they weren't contamination. Then there's the Rosetta mission, which found glycine, the simplest amino acid, swirling in the atmosphere of Comet 67P. These discoveries fuel the panspermia hypothesis, the idea that life's building blocks are cosmic hitchhikers scattered across the galaxy by cometary taxis. But panspermia isn't a magic bullet. Even if organic molecules rained down on early Earth, that's a far cry from a living cell. The leap from amino acids to self-replicating organisms is like going from a pile of bricks to a functioning city. No one knows exactly how it happened. Lab experiments like the famous Miller-Urey study show simple molecules can form under early Earth conditions, but cells require staggering complexity. Lipid membranes, RNA, proteins, all had to come together in perfect harmony, and the odds of that happening randomly are, well, astronomical. Then there's the durability problem. Space is a brutal place, freezing temperatures, vacuum, relentless radiation. Could delicate organic molecules survive millions of years in the void? Some extremophile microbes, like Deinococcus radiodurans, laugh in the face of radiation, repairing their shattered DNA like microscopic superheroes. If Earth's toughest life can endure Mars-like conditions, maybe microbial stowaways could survive interstellar journeys inside protective cometary ice. But here's the kicker: panspermia doesn't actually solve the origin problem. It just moves it somewhere else. If life didn't begin on Earth, where did it begin? A warmer, wetter Mars, a distant exoplanet with ideal chemistry? Or are we the product of countless cosmic accidents, a chain of chemical reactions spanning star systems? The answer might lie in our own genes. If we ever find extraterrestrial life and it shares our DNA structure, or lacks it entirely, that could reveal whether life has a universal blueprint or arose multiple times independently. Until then, the question lingers, as vast and open as space itself. every meteorite that lands, every comet we study, brings us closer to solving the ultimate mystery. Are we Earth's children or the universe's? In the vast silence of space, there are screams, brief, intense blasts of radio waves so powerful they outshine entire galaxies for mere milliseconds. These are fast radio bursts, or FRB, and they're one of the universe's most electrifying puzzles. First detected in 2007, these cosmic flashes arrive without warning, often vanishing before astronomers can pinpoint their origin. Some erupt once and never repeat. Others fire off like erratic cosmic lighthouses, flickering in patterns that defy explanation. Where does such titanic energy come from? The leading suspect is a magnetar, a neutron star with a magnetic field so strong it could strip the data from your credit card from halfway across the solar system. When these ultra-dense stellar corpses quake or flare, they might unleash FRBs as gravitational tsunamis ripple through their crusts, twisting magnetic fields into knots of raw energy. But magnetars might not be the whole story. In 2020, astronomers caught a break when an FRB erupted from our own galactic backyard, a magnetar known as SGR 1935 plus 215. The burst matched the profile of distant FRBs, suggesting at least some of these signals come from these magnetic monsters. Yet not all FRBs fit neatly into this box. Some repeat with clockwork precision, like FRB 1812, which blinks every 16.35 days like a celestial metronome. Others spit out bursts with energies equivalent to 500 million suns, far beyond what any known stellar object should produce. This unpredictability has fueled wilder theories. Could FRBs be evidence of alien propulsion systems, cosmic engines harnessing unimaginable power to push light sails across interstellar space? The idea isn't as far-fetched as it sounds. In 2017, the Breakthrough Listen project detected an FRB with a bizarre, sloped frequency pattern, sparking speculation about artificial origins. Most scientists dismiss this as unlikely, but the sheer strangeness of some bursts keeps the door cracked. Then there's the plasma lensing theory. Imagine a dense cloud of charged particles drifting between galaxies. When an FRB passes through, it could be magnified or distorted, like light bending through a frosted window. This might explain why some bursts appear brighter or fainter than expected, or why their signals sometimes arrive in multiple copies, staggered by milliseconds. The truth is, FRBs are a cosmic Rorschach test. What we see in them often reflects what we're willing to imagine. They could be the death cries of collapsing neutron stars, the reverberations of cosmic strings, or something entirely beyond our current physics. Every new detection peels back another layer of the mystery, revealing just how little we know about the universe's most violent whispers. And that's what makes them irresistible, not just as scientific puzzles, but as reminders that the cosmos still holds wonders we've yet to dream of. Spin a child's toy top and you instinctively understand the rules. The faster it rotates, the more force it takes to keep it from flying apart. Now picture that same principle scaled up to a galaxy, a swirling disk of billions of stars, gas and dust. Here's the catch: galaxies rotate so fast that, according to Newton's laws, they should tear themselves apart. The outer stars whip around at velocities that defy gravity's grip based on the visible matter alone. This cosmic conundrum is one of the strongest pieces of evidence for dark matter, the invisible glue holding galaxies together. But what if we've been missing something fundamental about gravity itself? Let's zoom in on a classic example, the Andromeda Galaxy. Its outer stars orbit at nearly 250 kilometers per second, a speed that should send them hurtling into the void. Yet they don't. The math only works if Andromeda is embedded in a vast halo of dark matter, its gravity anchoring those speeding stars. This pattern repeats across the universe, from spiral galaxies to dwarf galaxies, all spinning faster than the visible mass can explain. It's like watching a car race where the vehicles cling to the track despite no visible brakes or rails. Something unseen must be at work. Enter modified Newtonian dynamics. Proposed in the 1980s by physicist Mordechai Milgrom, suggests that at extremely low accelerations, like those in galaxy outskirts, gravity behaves differently than Newton or Einstein predicted. Instead of invoking dark matter, tweaks the equations so that gravity doesn't weaken as sharply over distance, giving stars the extra tug they need to stay bound. Think of it like adjusting a guitar string, too loose and the note flattens. Tweak the tension just right and the pitch holds. In some cases, predicts galaxy rotation curves with eerie accuracy, no dark matter required. But here's where the controversy ignites. Falters in galaxy clusters where visible matter alone can't account for the gravitational lensing effects we observe. Dark matter, meanwhile, elegantly explains not just galaxy rotations, but also the large-scale structure of the universe, like the cosmic web of filaments and voids. Then there's the bullet cluster, a cosmic collision where dark matter and visible matter were wrenched apart, leaving a gravitational shadow that struggles to explain without some hidden mass. So is dead? Not quite. A vocal minority of physicists argue that dark matter searchers have come up empty-handed for decades, and that successes hint at an undiscovered layer of gravity's nature. Others propose hybrid models. Perhaps dark matter exists, but gravity also behaves unexpectedly at galactic scales. The debate rages on, fueled by anomalies like ultra-diffuse galaxies that rotate suspiciously smoothly for their lack of visible mass. This isn't just academic squabbling. If is correct, it would upend centuries of physics, rewriting our understanding of one of the universe's fundamental forces. If dark matter prevails, its elusive nature challenges us to invent new ways of seeing the invisible. Either way, the mystery of galaxy rotation reminds us that the cosmos still has cards left to play, and the rules of the game might be stranger than we thought. Imagine crushing the entire mass of Mount Everest into a single sugar cube. That's the kind of incomprehensible density we're dealing with inside a neutron star, the collapsed core of a giant star that didn't quite become a black hole. These cosmic dead ends pack 1.5 times the sun's mass into a sphere no wider than Manhattan, creating conditions so extreme they warp the very rules of matter itself. What happens to atoms under that kind of pressure? The answer might rewrite physics as we know it. At the surface, neutron stars are already bizarre enough. A crust of iron atoms squeezed into a crystalline lattice so tight electrons merge with protons, forming a sea of neutrons. But dive deeper and things get stranger. As gravity overwhelms even nuclear forces, neutrons themselves begin to break apart, dissolving into a swirling soup of their own building blocks, quarks and gluons. This is quark-gluon plasma, a state of matter that hasn't existed freely since the universe's first microseconds after the Big Bang. Here, the usual boundaries between particles blur. Protons and neutrons lose their identity, becoming a churning, ultra-dense fluid where quarks, normally eternally confined, roam almost freely. Now push further toward the core, where pressures may exceed 100 trillion times Earth's atmosphere. Some theories suggest quarks here could undergo a metamorphosis, transforming into strange quarks, a heavier, exotic variant normally seen only in high-energy particle collisions. If this happens, the entire star might convert into strange matter, a hypothetical substance more stable than anything in our universe. One speculative idea even proposes that strange matter could be infectious. A single droplet touching ordinary matter might catalyze its conversion, like cosmic ice 9 from Kurt Vonnegut's fiction. Could neutron star cores be hiding even wilder secrets? Quantum chromodynamics, the theory governing quark behavior, predicts that under extreme enough conditions, quarks might pair up into Cooper pairs, creating a superfluid, a frictionless state where matter flows without resistance. Combine that with the star's insane rotation, speed some spin hundreds of times per second, and you've got a vortex of superfluid neutrons and quark soup, potentially generating immense magnetic fields or even gravitational waves. Then there's the darkest possibility. At the very center where equations break down, some models suggest a singularity might lurk, not as destructive as a black hole's, but a dense knot of spacetime curvature. Others propose quantum tunneling could create temporary wormholes, fleeting portals to other parts of the universe. Neutron stars are cosmic laboratories, testing the limits of our understanding. Every glitch in their rotation, every X-ray burst they emit, carries clues about the physics of the impossible, and that's what makes them so thrilling. They're not just dead stars. They're puzzles waiting to be solved, holding answers to questions we haven't even thought to ask yet. In the vast emptiness between the stars, two tiny spacecraft, Pioneer 10 and 11, were defying the laws of physics. Launched in the early 1970s, these trailblazers were the first human-made objects to venture beyond the asteroid belt, equipped to study Jupiter and Saturn before hurtling toward interstellar space. But as they drifted farther from the Sun, something strange happened. Their speed didn't match NASA predictions. An unknown force was tugging them backward, slowing them ever so slightly, just enough to baffle scientists for decades. This was the Pioneer anomaly, a gravitational mystery that refused to fade away. At first, the numbers seemed like a glitch. The spacecraft were decelerating by about 300 microns per second squared, a whisper of a slowdown equivalent to the weight of a single snowflake pressing against your palm. But in the precision-driven world of orbital mechanics, even the tiniest discrepancy demands an explanation. Theories flew fast. Was it dark matter dragging on the probes? A flaw in our understanding of gravity itself, or something as mundane as a fuel leak? Each possibility crumbled under scrutiny. Dark matter's pull would have affected other spacecraft like Voyager, which showed no such anomaly. And fuel leaks couldn't account for the consistent unidirectional tug. Then came the thermal hypothesis, Pioneer's nuclear power source, a plutonium-filled artery constantly emitted heat. If that radiation weren't perfectly symmetrical, it could create a tiny but measurable thrust in the opposite direction, like a campfire's warmth nudging a nearby pebble. Computer models suggested uneven heat distribution from the spacecraft's design, its dish antenna blocking some radiation while the rest escaped asymmetrically. By 2012, after painstaking analysis of decades-old engineering blueprints, researchers declared the case closed. Thermal radiation was the culprit. But not everyone was convinced. Critics pointed out that the heat explanation only accounted for about 2/3 of the observed deceleration. What about the rest? Some physicists speculated about quantum vacuum effects, the idea that empty space isn't truly empty, but a frothing sea of virtual particles that might interact with the probes. Others floated wilder ideas, like a subtle error in Einstein's theory of general relativity that only manifests over vast distances. The real lesson of the Pioneer anomaly isn't just about a few misplaced decimal points. It's a humbling reminder that even in the era of precision cosmology, the universe can still surprise us. For 30 years, these aging probes whispered secrets we couldn't quite decipher, proof that sometimes the smallest mysteries linger the longest. And who knows, maybe out there in the dark, the Pioneers are still carrying a puzzle we haven't even thought to solve yet. Black holes come with a built-in no-peeking rule, the event horizon, a boundary so absolute that nothing, not even light, can escape its grip. But what if that cosmic curtain could be torn away, exposing the singularity within? Enter the most scandalous idea in gravitational physics, naked singularities. Unlike their well-behaved Kerr black hole cousins, which dutifully hide their infinitely dense cores behind event horizons, naked singularities would flaunt their space-time warping cores for the entire universe to see. And that's a problem. The cosmic censorship hypothesis proposed by physicist Roger Penrose suggests nature abhors such exhibitionism. It's the universe's way of protecting causality, ensuring that singularities where gravity becomes infinite and physics breaks down remain safely tucked behind event horizons. Without this cosmic firewall, unpredictable chaos could leak into the universe. Imagine a gravitational free-for-all where time loops back on itself, where cause and effect unravel like a poorly written time travel plot. That's the nightmare scenario naked singularities threaten to unleash. But could they actually exist? Kerr black holes, named after mathematician Roy Kerr, are the gold standard for spinning black holes. Their event horizons and ergospheres, regions where spacetime gets dragged like taffy, keep their singularities discreetly veiled. Yet some solutions to Einstein's equations suggest that under extreme conditions, say, a black hole spinning at the absolute limit of stability, the event horizon might vanish, leaving the singularity naked. Here's where things get contentious. Simulations of collapsing stars or colliding black holes occasionally spit out naked singularities in their equations, like glitches in reality's code. But are these mathematical artifacts, or do they hint at genuine cosmic possibilities? Opponents argue that quantum effects or unforeseen physics would always intervene, preventing such exposures. After all, we've never observed a naked singularity, though some speculate that certain gamma-ray bursts or unexplained gravitational lensing events could be candidates. The debate cuts to the heart of whether the universe plays by orderly rules or tolerates gravitational anarchy. If naked singularities exist, they'd be more than cosmic oddities. They'd be portals to a realm where predictability dies, where spacetime itself becomes a lawless frontier. For now, they remain tantalizing ghosts in the equations, daring us to prove whether they're forbidden by nature's design or just waiting to be found. The universe has been expanding since the moment of the Big Bang, but where is it all headed? Will this grand cosmic story end with a whisper, a crunch, or a violent tear? The answer hinges on a mysterious force we barely understand: dark energy, the invisible driver pushing galaxies apart at an ever-increasing rate. One possibility is the Big Freeze, also known as heat death. Picture a universe where expansion never stops. Galaxies drift so far apart that their light can never reach one another. Stars burn out, black holes evaporate, and matter itself decays into faint radiation over trillions of years. Space becomes an unimaginably vast, cold, and empty graveyard where no new structures form, no energy flows, and time loses all meaning. It's the ultimate entropy, a slow, silent fade into darkness. But what if dark energy isn't constant? Some theories suggest it could weaken over time, allowing gravity to regain control. That's the Big Crunch scenario, a cosmic reversal where the expansion halts, then collapses inward. Galaxies rush back together, temperatures soar, and the universe contracts into an ultra-dense state, possibly triggering a new Big Bang. It's a cyclical vision, like a phoenix dying in flames only to be reborn. Yet recent measurements of dark energy's strength suggest it's not fading. If anything, it might be growing more dominant, making a crunch seem unlikely. Then there's the most dramatic finale, the Big Rip. If dark energy's repulsive force keeps intensifying, it wouldn't just push galaxies apart, it would overpower every binding force in nature. First, galaxy clusters would be shredded, then individual galaxies. Stars would be ripped from their orbits, planets torn from their suns. In the final moments, even atoms would be wrenched apart, nuclei split by the unstoppable stretching of spacetime itself. The universe wouldn't just end, it would unravel violently, piece by piece. So which fate awaits us? The answer lies in dark energy's true nature. Is it a constant force, as Einstein's cosmological constant suggested? Or does it evolve, growing stronger or weaker over time? Right now, observations favor the Big Freeze, but with so much about dark energy still unknown, the final chapter of the universe remains wide open. One thing's certain: the end won't be boring. Whether it's a slow fade, a fiery rebirth, or a catastrophic shredding, the cosmos has a flair for the dramatic. And we're lucky enough to live in the brief sliver of time where we can even ponder the question: Imagine two coins flipped simultaneously on opposite sides of the universe, yet somehow, every time one lands heads, the other instantly lands tails, no matter how far apart they are. This isn't magic, it's quantum entanglement, the phenomenon Einstein famously dismissed as spooky action at a distance. At its heart lies a paradox that shakes the foundations of reality. Entangled particles seem to communicate faster than light, defying our deepest notions of locality, the idea that objects can only be influenced by their immediate surroundings. Take the classic experiment with entangled photons. Measure one's polarization here on Earth, and its partner, even if light years away, snaps into a correlated state instantaneously. Not at the speed of light instantly, as if space and time don't apply. Einstein hated this, arguing it violated relativity's cosmic speed limit. He insisted there must be hidden variables, unknown properties predetermined at the moment of entanglement, like a pair of gloves split between two boxes. Open one to find a left hand, and you know the other holds a right, no spookiness required. But in the 1960s, physicist John Bell proved otherwise. His inequalities showed that if hidden variables existed, entangled particles couldn't correlate as strongly as experiments later confirmed. The universe, it seems, really does permit this eerie connection. So what's really happening? One interpretation leans on the many worlds theory. Every measurement doesn't collapse quantum possibilities but splits reality into branches. In one world, your photon is vertically polarized. In another, it's horizontal. Entanglement, then, isn't action at a distance. It's a cosmic synchronization across parallel universes. Then there's pilot wave theory, a modern revival of de Broglie's idea that particles are guided by invisible pilot waves. Entangled particles aren't communicating, they're dancing to the same underlying rhythm, like boats bobbing in tandem on a hidden pond. The most radical answer, reality itself might be fundamentally non-local. Space and time could be emergent illusions with deeper layers of the universe connected in ways we can't yet perceive. It's as if the cosmos is a hologram where every part contains whispers of the whole. This isn't just philosophy. Researchers are testing these ideas with ever more precise experiments, from loophole-free Bell tests to entanglement swapping across satellites. Each result edges us closer to a truth that might rewrite physics. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and entanglement is its most tantalizing clue. Reach out and grab the space around you. Go ahead, what do you feel? Nothing, that's the illusion. The vacuum of space, that seemingly perfect void between stars, isn't empty at all. It's a seething, bubbling cauldron of activity where the very fabric of reality writhes with energy. Quantum mechanics paints a picture so bizarre that even the word empty loses all meaning. At the smallest scales, spacetime isn't smooth. It's a turbulent quantum foam where tiny bubbles of spacetime constantly form and vanish, like a fizzy soda at the Planck length, a scale so small, a single atom looks like a galaxy in comparison. These fleeting distortions aren't just mathematical quirks. They might hold the key to understanding black holes, wormholes, even the birth of the universe itself. Imagine the cosmos as an ocean, its surface calm to our eyes, but zoom in, and you'll see it's made of countless chaotic ripples. Then there's the zero-point energy field, the universe's baseline hum. Even at absolute zero, when all classical motion stops, space thrums with residual energy. It's the reason helium stays liquid at temperatures that freeze hydrogen solid. This energy prevents atoms from ever fully settling. But the real shocker, this isn't some faint background whisper. Calculations suggest the energy in a single cubic meter of empty space could boil all Earth's oceans. Why don't we feel it? Because it's everywhere, equally balanced, like an invisible weight pressing inward from all directions. Now meet virtual particles, the universe's ultimate loophole. Borrowing energy from the vacuum, particle-antiparticle pairs blink into existence for fractions of a nanosecond before annihilating. Normally, they're phantoms, undetectable. But near a black hole's event horizon, things get wild. One particle gets swallowed while the other escapes as real radiation, Hawking radiation, the slow leak that dooms black holes to evaporate over eons. Here's the kicker: this process suggests even nothing is creative, constantly birthing and destroying particles in a dance older than time. So is empty space a myth? Absolutely. The void is alive, a dynamic stage where reality itself flickers in and out of existence. What we call nothing might be the most something there is, the hidden engine driving everything from cosmic expansion to the very glue holding atoms together. The next time you gaze at the night sky, remember, the true marvel isn't just the stars, it's the frenetic, invisible symphony playing in the darkness between them. If black holes are cosmic vacuum cleaners, sucking everything in beyond the point of no return, then white holes are their theoretical opposites, celestial fire hydrants blasting matter and energy outward with unstoppable force. Imagine a black hole running in reverse, where instead of an event horizon trapping everything inside, there's a no-entry boundary that nothing can cross into. It's a one-way door to the universe, spewing out light, particles, and radiation with no way back in. The math behind general relativity allows for such objects, but here's the catch. While black holes are inevitable endpoints for collapsing stars, white holes would have to be impossibly fine-tuned cosmic miracles, violating the second law of thermodynamics by decreasing entropy over time. Think of it like pressing rewind on a video of a black hole's life. A white hole would start as a singularity, already a controversial concept, before exploding outward in a burst of energy, essentially becoming a Big Bang in miniature. Some theories even suggest that a white hole could be the other end of a black hole's tunnel, connecting them through an Einstein-Rosen bridge. But if that's true, why haven't we seen one? The universe is littered with black holes, from stellar mass ones peppering galaxies to supermassive beasts anchoring galactic centers. White holes, by contrast, are entirely hypothetical. No telltale bursts of energy, no bizarre gravitational signatures, no inexplicable cosmic geysers of matter match their predicted behavior. One explanation is that white holes are inherently unstable. Unlike black holes, which form naturally from dying stars, white holes would require some exotic mechanism to reverse the flow of time, or at least mimic its effects. Quantum gravity models hint that a black hole's eventual evaporation via Hawking radiation could, in principle, birth a white hole, recycling the trapped matter back into the universe. But even this process would take far longer than the current age of the cosmos, leaving any potential white holes firmly in the realm of not yet. Then there's the observational paradox. If white holes exist, they should be dazzlingly bright, ejecting energy at levels that would make quasars look like candles. Yet the sky shows no obvious candidates. Some have speculated that gamma-ray bursts, those fleeting, hyper-energetic explosions, could be white holes blinking into existence and vanishing, but the evidence is non-existent. Others argue that white holes might disguise themselves as ordinary phenomena, like pulsars or active galactic nuclei, hiding in plain sight. The most compelling argument against white holes isn't observational silence, though, it's thermodynamics. The universe tends toward disorder, and white holes, by definition, would defy that trend, ejecting perfectly ordered energy without any input. It's like expecting a shattered vase to spontaneously reassemble itself. Still, the mere possibility of white holes tantalizes physicists because they force us to confront the limits of general relativity and ask, does time's arrow always point forward, or are there places or moments where it flips? For now, white holes remain ghostly outliers in the equations, reminding us that the universe's rulebook might still have pages we haven't turned. The moon shouldn't exist. At least, not as we know it. Earth's closest neighbor is a cosmic paradox, geologically similar enough to suggest a shared origin, yet chemically distinct in ways that defy easy explanation. The leading theory, the giant impact hypothesis, paints a violent origin story. 4.5 billion years ago, a Mars-sized protoplanet named Theia slammed into the young Earth, vaporizing rock and metal in a cataclysmic collision. Debris from this impactor and Earth-shattered mantle orbited our planet, eventually coalescing into the Moon. Computer simulations show this scenario perfectly explains the Moon's lack of a substantial iron core. Theia's dense metallic heart would have plunged into Earth's core during impact, leaving the lunar disk iron poor. But here's the puzzle. If the Moon formed primarily from Theia's remnants, its composition should differ significantly from Earth's. Yet Apollo mission samples revealed eerie similarities. Oxygen isotopes in lunar rocks match Earth's with uncanny precision, like two glasses of water poured from the same pitcher. This shouldn't happen unless Theia was somehow Earth's isotopic twin, a statistical improbability given the diversity of planetary building blocks in the early solar system. Some scientists propose a high-energy impact so extreme it thoroughly mixed Earth and Theia's material before the Moon condensed, creating a homogenized blend. Others suggest Theia might have formed unusually close to Earth in the protoplanetary disk, sharing its isotopic signature from birth. Then there's the mystery of the Moon's missing volatiles, elements like sodium and potassium that vaporize easily. Compared to Earth, the Moon is bone dry, with these elements depleted by factors of 10 to 100. The giant impact's heat should have boiled them off, yet some volatiles remain clustered in unexpected ways. Recent studies of lunar volcanic glass beads hint at water trapped deep in the Moon's mantle, complicating the narrative further. Did some volatiles survive the impact hidden in mineral structures, or were they delivered later by comets? The plot thickens when you examine the Moon's far side. China's Chang missions revealed stark differences in crustal thickness and composition between the familiar near side and the hidden far side, a dichotomy the Theia impact alone can't explain. Some models propose a second, smaller moon once shared Earth's orbit, eventually colliding with our Moon to create this lopsided geology. Others point to Earth's gravitational pull, which may have concentrated certain minerals on the near side like a cosmic sorting machine. Every new lunar sample, every refined simulation peels back another layer of this 4.5 billion-year-old mystery. The Moon isn't just a celestial time capsule, it's a mirror reflecting back questions we're only beginning to ask. And until we crack its code, our closest companion in the cosmos remains one of its most enigmatic. On the night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so strong and unusual that astronomer Jerry Amon circled it on the printout and scrawled, "Wow." In the margin, the burst lasted 72 seconds, exactly the length of time the telescope's receiver could hold a signal in its field of view as Earth rotated. It came from the direction of the constellation Sagittarius, blasting at a frequency of 1,420 MHz, a radio band where hydrogen, the most common element in the universe, naturally resonates. And then it vanished, no repetition, no trace, just one tantalizing blip that's haunted astronomers ever since. Here's what makes the WOW signal so compelling. It wasn't random noise. The signal followed a precise intensity curve, rising, peaking, then falling exactly as you'd expect if it came from a distant point in space passing through the telescope's beam. And that frequency, 1,420 MHz, is smack in the water hole, a quiet band between hydrogen and hydroxyl radiation that some scientists consider an ideal channel for interstellar communication, like picking a clear spot on the radio dial where cosmic static won't drown you out. So what could it have been? The leading natural explanation is a hydrogen cloud excited by a passing comet, except no known comets were in that region of the sky that night. Others suggest a military satellite or experimental transmission, but declassified records show no human activity matching the signal's profile. Then there's the extraterrestrial hypothesis. If aliens were deliberately signaling, a brief, high-powered burst makes strategic sense. It's energy efficient, and the narrowband frequency suggests artificial tuning. But why no repeat? Even the most patient civilization would likely send follow-ups unless the signal was never meant for us in the first place. A misaligned beacon intended for another star system, perhaps. The real frustration is the lack of data. The Big Ear telescope that detected the signal was dismantled in 1997, and despite decades of searching with modern equipment, including SETI-targeted scans of the same coordinates, nothing like it has ever been found again. Some argue this silence is telling. Maybe it was a fluke, a cosmic one-off we'll never explain. Others point to the sheer vastness of radio frequencies and directions we'd need to monitor continuously to catch another such blip. It's like trying to find a specific grain of sand on every beach on Earth while blindfolded. The WOW signal endures not just as a mystery, but as a symbol. In a universe that so often feels indifferent, it's a fleeting hint that someone or something might be out there reaching across the void. Whether it was aliens, a freak cosmic event, or something else entirely, it reminds us that the cosmos still has the power to stop us in our tracks and make us say, wow. Imagine a single subatomic particle hurtling through space with the kinetic energy of a fast-pitched baseball, packed into something a billion times smaller than a grain of sand. This isn't science fiction, it's the reality of ultra-high-energy cosmic rays, dubbed "oh my God" particles after their discovery in 1991 left researchers speechless. These rogue protons or atomic nuclei travel at over 99.9999999% the speed of light, carrying energies exceeding 100 exaelectron volts, millions of times more powerful than anything our most advanced particle accelerators can produce. And here's the kicker, we have no idea what cosmic powerhouse could possibly launch them. The mystery begins with their journey. Cosmic rays are charged particles, which means they should be deflected by the galaxy's magnetic fields, zigzagging unpredictably like pinballs. Yet when we trace the paths of the highest energy ones backward, they point to voids, empty regions of space where no known astrophysical monsters like active galactic nuclei or supernova remnants exist to serve as natural particle cannons. Even stranger, at these insane energies, particles should lose steam by smashing into the cosmic microwave background radiation, the afterglow of the Big Bang, an effect called the Greisen-Zatsepin-Kuzmin cutoff. The fact that oh my God particles reach us at all suggests some cosmic sneaky trick is at play. So what's slinging these particles at us? One radical contender is gamma ray, bursts, the universe's most violent explosions, capable of outshining entire galaxies for seconds. If their relativistic jets can focus energy tighter than a laser beam, they might accelerate particles to these extreme velocities. Then there's supermassive black holes at galaxy cores, where magnetic fields near the event horizon could act like enormous slingshots. Some theories even invoke exotic physics, like cosmic strings, hypothetical defects in spacetime, left over from the early universe, snapping and releasing bursts of energy that make supernova look like firecrackers. But the plot thickens. In 2021, the Telescope Array project in Utah detected another oh my God particle with a footprint spanning 23 square kilometers, yet its origin remains ghostly. Unlike light, cosmic rays don't travel in straight lines, and their sources could be billions of light years away, their trails scrambled by magnetic fields. It's like trying to find a sniper by studying the bullet's impact while ignoring the wind. Every clue comes warped by forces we can't fully map. The real puzzle isn't just how these particles get their speed, but why they're so rare. For every oh my God particle that hits Earth's atmosphere, countless others miss us entirely, a cosmic needle in a haystack. Catching them requires sprawling detector arrays like the Pierre Auger Observatory in Argentina, where 1,600 tanks of ultra-pure water wait for the telltale blue glow of particle showers cascading down from the upper atmosphere. Even then, each detection raises more questions than answers. What's at stake goes beyond astrophysics. If we can decipher these natural particle accelerators, we might unlock new fundamental physics, perhaps even secrets about dark matter or extra dimensions. For now, every ultra-high-energy cosmic ray is a message in a bottle from the universe's most extreme environments, carrying clues we're only beginning to decode. And until we crack their origin, they'll remain both a testament to nature's power and a humbling reminder of how much we have yet to learn. In the constellation Cygnus, about 1,500 light-years away, a star named KSE 8462852, better known as Tabby's star, has been playing a cosmic game of peekaboo with astronomers. Unlike the steady pulse of most stars, Tabby's star dims erratically, sometimes dropping in brightness by up to 22% before snapping back to normal. These aren't the predictable, symmetrical dips caused by orbiting planets. Instead, they're chaotic, irregular, and completely baffling, so much so that when astronomer Tabitha Boyajian first documented the phenomenon in 2015, even the most conservative scientists found themselves whispering a tantalizing question: could this be an alien megastructure? The idea wasn't pure science fiction. Physicist Freeman Dyson had speculated decades earlier that advanced civilizations might harness stellar energy by building vast arrays of solar collectors, Dyson swarms, encircling their host star. Tabby's star's weird dimming pattern seemed to fit. Maybe, just maybe, we were glimpsing the shadows of colossal construction projects, partially blocking the star's light as they orbited. The internet erupted. For a brief, electrifying moment, the hunt for extraterrestrial intelligence felt closer than ever, but science thrives on skepticism. Alternative explanations emerged, the most compelling involving dust, not alien engineering, but vast, uneven clouds of it. Observations revealed the dimming was more pronounced at shorter wavelengths, a telltale sign of fine particles scattering blue light, just like Earth's atmosphere reddens the setting sun. Further studies suggested swarms of cold, clumpy debris, perhaps the remnants of a shattered planet or colliding comets, drifting in eccentric orbits around the star. Yet even this dusty explanation leaves puzzles. Tabby's star's long-term dimming and overall fade of about 3% per century defies simple models. Some researchers propose a recent collision between planetary bodies, ejecting enough debris to create both the short-term dips and the slow, lingering haze. Others wonder if the star itself is unstable, prone to bouts of internal activity that throw off immense plumes of obscuring material. The truth is, Tabby's star refuses to fit neatly into any box. It's a cosmic Rorschach test, revealing more about our hopes and methods than its own nature. For now, it remains an enigma, one that reminds us the universe is stranger, messier, and more wonderful than even our wildest theories. Whether the answer lies in dust, aliens, or something entirely unforeseen, the mystery endures, pulling us deeper into the unknown with every flicker of its elusive light. In the vast cosmic ocean, most galaxies blaze with the light of billions of stars, their shapes sculpted by dark matter's invisible hand, but not these. Ultra-diffuse galaxies float like pale ghosts, stretching as wide as the Milky Way while containing just 1% of its stars. Their faint glow barely outshines the background sky, yet their very existence throws a wrench into our understanding of how galaxies form. The real shocker, some seem to have almost no dark matter at all. That's like finding a ship with no hull somehow still afloat. Take Dragonfly 44, discovered in 2016. This gauzy smudge in the Coma cluster weighs about as much as the Milky Way, but 99.99% of that mass should be dark matter, except it isn't. Observations revealed stars moving so sluggishly that barely any unseen mass could be anchoring them. This flips the script on decades of galaxy formation theory, where dark matter acts as gravitational scaffolding, pulling gas together to birth stars. Without it, ultra-diffuse galaxies shouldn't exist, let alone survive the tidal forces of crowded galaxy clusters. So where did these cosmic wraiths come from? One camp argues they're failed galaxies' primordial clouds that never gathered enough gas to light up properly. Picture a stunted tree in a crowded forest, choked out before it could grow. Others propose they're the shredded remains of normal galaxies, their dark matter stripped away by violent encounters. Imagine a dandelion hit by a hose blast, leaving only the wispy seeds behind. There's just one problem. Some ultra-diffuse galaxies live in isolation, far from the galaxy cluster carnage that could explain their missing mass. Then there's the nuclear option. Maybe our understanding of gravity itself is flawed. Modified Newtonian dynamics, or MUND, suggests gravity behaves differently in ultra-low-density environments, eliminating the need for dark matter in these galaxies. But if MUND is right, why do most galaxies still fit the dark matter model? It's like having one set of physics for cities and another for deserts. The most tantalizing clue might lie in their star-forming oddities. Some ultra-diffuse galaxies are cosmic dead zones, their gas spent eons ago. Others, like NGC 1052DF2, bizarrely churn out new stars despite their ghostly appearance. This diversity hints that multiple formation paths might exist, each leaving galaxies ethereal for different reasons. Every new discovery deepens the mystery. Recent observations even suggest some ultra-diffuse galaxies might be freakishly rich in dark matter, adding another layer of confusion. Are we looking at multiple galactic species mistakenly grouped together, or does their very existence point to gaping holes in our cosmic playbook? For now, these faint, sprawling enigmas float through the darkness, whispering questions we're just beginning to hear. We take for granted that our world operates in three spatial dimensions: length, width, height plus time. But what if reality is like an unopened origami sculpture, hiding folds and creases we can't yet see? String theory, the leading candidate for a theory of everything, insists the universe actually has 10 dimensions, maybe even 11. The catch: these extra dimensions are curled up tighter than a clenched fist, existing at scales so small they evade our senses. Imagine an ant crossing a telephone wire. From afar, the wire seems one-dimensional, but up close, the ant senses the wire's full cylindrical form. Could our cosmos be similarly deceiving us? The Large Hadron Collider, humanity's most powerful microscope, has been hunting for traces of these hidden realms. One clue could be the mysterious disappearance of energy during particle collisions, like a cosmic magic trick where gravity, the weakest force, slips into other dimensions. In our familiar 3D world, gravity's strength diminishes with distance, following the inverse square law. But if gravity leaks into extra dimensions, it could drop off faster, like water draining through unseen holes. The LHC's detectors scour debris from proton smash-ups for exactly these anomalies, hoping to spot missing energy signatures that hint at gravity's secret escape routes. Then there's the brain world scenario, a mind-bending offshoot of string theory. Picture our universe as a four-dimensional membrane or brain floating within a higher dimensional space. Ordinary matter and light might be glued to our brain, but gravity, acting like an untethered force, could propagate into the bulk. This could explain why gravity is exponentially weaker than other forces, its strength diluted across dimensions we can't access. Some versions even suggest black holes might be gateways between brains, their singularities punching microscopic tunnels into adjacent realities. Critics argue these ideas flirt with untestable speculation. After all, if extra dimensions are compactified at the Planck scale, 10 to the power of -35 meters, no instrument today can probe them directly. Yet hopeful theorists counter that some dimensions might be large relative to quantum scales, perhaps a millimeter wide, detectable through tabletop experiments measuring gravity's behavior at microscopic distances. So far, no dice, but the search continues. Whether these dimensions exist or not, their mere possibility reshapes how we see reality. The universe might be a vast, layered labyrinth, its true architecture hidden in plain sight. And that's the thrill. Science isn't just about answering questions. It's about discovering how much bigger the questions can get. At the heart of modern physics lies a rift so profound it's been called the greatest unsolved problem in science, the stubborn refusal of gravity to play by the same rules as the quantum world. On one side stands Einstein's masterpiece, general relativity, which paints gravity as the elegant curvature of spacetime, where planets and stars dance along invisible geodesics. On the other lies quantum field theory, a realm where particles pop in and out of existence, governed by probabilities and forces exchanged via ghostly messenger particles. Both theories work flawlessly in their own domains, but bring them together, say, near the singularity of a black hole or the first moments of the Big Bang, and the equations explode into nonsense. It's like trying to combine Shakespeare with quantum chemistry. The languages are fundamentally incompatible. Take the simple act of an apple falling from a tree. In Einstein's universe, this happens because the apple follows the curve of spacetime bent by Earth's mass. But zoom into the quantum scale, and gravity vanishes from the equations altogether. The other forces, electromagnetism, the strong and weak nuclear forces, are all mediated by particles like photons and gluons. Gravity alone has no quantum counterpart. Hypothetical gravitons might fill this gap, but they've never been detected, and attempts to squeeze them into quantum frameworks produce infinite values, as if the math itself is screaming in protest. Enter the contenders vying to bridge this divide. Loop quantum gravity takes a minimalist approach, arguing that spacetime isn't smooth and continuous but woven from tiny, indivisible loops. Think of the universe as a cosmic tapestry where each thread represents a plank-sized stitch in the fabric of reality. In this view, gravity emerges from the interactions of these loops, avoiding singularities by preventing spacetime from being divided infinitely. Black holes, for instance, might not crush matter into oblivion but rebound it in a quantum bounce, like a compressed spring finally released. String theory, meanwhile, goes maximalist. It proposes that all particles are actually vibrating strings, with their harmonies determining whether they manifest as electrons, quarks, or perhaps gravitons. To make the math work, these strings dance not in 3 dimensions but 10 or 11, with the extra dimensions curled up into shapes called Calabi-Yau manifolds, complex geometries smaller than atoms. Here, gravity isn't separate but just another note in the string's symphony, unified with other forces at energies so high they've only existed once, the Big Bang's first moments. The clash between these frameworks isn't just technical, it's philosophical. Loop quantum gravity prioritizes spacetime's structure, staying closer to Einstein's geometric vision. String theory seeks a grand unification, often at the cost of introducing unobservable dimensions and a nearly infinite number of possible universes. Critics call string theory not even wrong because its predictions lie beyond current experimental reach, while loop quantum gravity struggles to explain how smooth spacetime emerges from its discrete building blocks. Yet the stakes couldn't be higher. Unifying these theories wouldn't just tidy up textbooks, it might reveal hidden layers of reality, from the true nature of black holes to the origin of the universe itself. Until then, physicists are left with a cosmic jigsaw puzzle, knowing the pieces must fit but unable to see the full picture. And that's the beauty of the mystery. Somewhere in the chaos of competing equations, the universe is holding its breath, waiting for us to catch up. We've journeyed through 30 of the universe's most baffling mysteries, questions that defy our best theories, challenge our understanding of reality, and remind us just how much we have yet to discover. From the eerie silence of the Fermi paradox to the phantom tug of dark matter, from the quantum riddles of entanglement to the cosmic censorship of black holes, each mystery is a frontier waiting to be crossed. These aren't just gaps in our knowledge, they're doorways to new physics, invitations to rethink everything we thought we knew. Think about it. Every great leap in science began with a question that seemed unanswerable. Newton wondered why the apple fell and gravity entered the equation. Einstein asked what it would be like to ride a beam of light and space-time bent to his vision. The puzzles we've explored today aren't dead ends, they're sparks. The next revolutionary idea might be hiding in the chaos of a singularity, the flicker of a fast radio burst, or even your own curiosity. So stay wonderstruck, look up at the night sky and let the questions simmer. Maybe you'll be the one to crack the code of dark energy or stumble upon a clue that unravels the multiverse. Science isn't just a collection of facts, it's a conversation, a collective pursuit of the unknown. And the most exciting part, the universe isn't done surprising us. Every unanswered question is a promise. There's more to find, more to explore, more stories waiting to be told. The cosmos doesn't give up its secrets easily, but that's what makes the hunt exhilarating. Whether you're a seasoned stargazer or just starting to ponder the big questions, remember, the greatest discoveries begin with a simple thought: what if? Keep asking, keep dreaming. The next chapter of the universe's story might just have your name on it.